Hi, my name is Haresh Advani, and today we'll be reviewing the basics of Kubernetes. This series of lessons is for beginners wanting to get a foundation on Kubernetes and related technologies such as micro apps, containerization, Docker, and general micro app networking 101. Let's start with what is Kubernetes? Kubernetes is an orchestrator. It is definitely not a simple topic. In fact, Kubernetes is a very advanced add-on to an already complex technology. So before we begin to try to understand what Kubernetes is, we really need to discuss other critical prerequisites before getting into too much detail on Kubernetes. If you already know all this, then forgive me, but these particular video lessons are geared toward beginners. And again, for anyone who wants a fundamental understanding, this is being explained at a level 100. So I will provide higher level training in the future, but I have found that in general, the fundamentals are critical if anyone hopes to achieve a higher level of knowledge. Kubernetes is the most popular container orchestration tool. So let's talk about what this actually is. But let's first understand what is an orchestration tool and why do we need it. To understand this, you have to appreciate that Kubernetes as a system was really built by Google probably over more than 10 years of them using Borg to manage their own very large compute environments. Now, finally, in 2014, it was made public, and that's when Kubernetes was born. As an orchestrator, Kubernetes automates and controls large clusters or farms of containers. And as you can see, it's going to be critical for you to understand what a container is, why we need containers, and really a lot of information about containers to really appreciate why you need Kubernetes. Kubernetes provides a way for us to maintain a desired state of our infrastructure by use of declarative YAML configuration files. These declarative YAML config files specify many things, such as the image for the container, the number of instances you want to have, for example, the replicas, and other details about the software that's running in the container. Now, Kubernetes can run on-prem or really in any cloud. Kubernetes can run on a single host computer such as Linux, but by default, it is designed to keep its control components on a physically separate server than the additional servers on which applications will run. This is just for protection of the control plane, and in general, your environment, production environment, will need more than one server. So for this reason, it's typically recommended to have at least 3 Linux servers to host a cluster. In production, as many companies do, they potentially will have hundreds or even thousands of servers running in their cluster, or perhaps multiple clusters. Kubernetes provides automation and management of these clusters by enforcing rules which you set via these configuration files. These config files are mostly written in YAML and specify the application, the number of instances, and really as much detail as you need to provide, such as, for example, the RAM and other resources for each instance of this app. Now, each app instance I'm referring to is run as an independent container. Because it's critical for you to have a good fundamental understanding, let's get into these prerequisite details for things like containers, Docker, deployments, services, Kubernetes networking before we really go too far into Kubernetes. So let's talk about containers. What is a container? A container is smaller than a virtual machine. It's basically just an application running in a sandboxed environment and stored together with all its dependencies. Now, it does run on an operating system, but it shares the operating system, but in an isolated way from other containers. Now, if we contrast this to a virtual machine, you can see that we have a few layers extra when running virtual machines, such as the hypervisor, such as an operating system, and then usually in a VM, you have an operating system and then you run the application. With containers, you reduce the hypervisor layer and the OS layer, which is not needed for every container. This provides for many efficiencies as well as higher portability than a virtual machine. And it also provides for less dependence on the operating system the container is running on. So if you see here on docker.com, you could see their descriptions of how this works, that you have your infrastructure, you do have a host operating system, but then immediately on that, you have Docker. Let's go down a little bit further, and I'll show you something on this, how it contrasts to a virtual machine. If you look at the right side of the screen here, you do have your hardware that you run, hardware or software if you're running a virtual machine. But the point is you have infrastructure on which the systems will run. But in the case of the virtual machine on the right, you also have an operating system along with this hypervisor. And then finally you get to put on apps. If you look at the left side of the picture here, you have your infrastructure, you have your host operating system such as Linux, but then you put Docker on that. And right on Docker, you have these different apps running that are isolated from each other. So there is a reduction where you don't have the hypervisor and you don't have the multiple operating systems that you do on a normal VM environment. Now, another way to look at this is that they're efficient little environments used to store data and run applications. They're secure and they're resource independent. So containers are basically a package of files that are run as a set, and they're kept separate from other containers. To help gain a fundamental understanding of this, think of a folder of files, and the folder contains all that's needed to execute an instance of the app. So let's say if you're thinking of a Windows environment, you'd have an exe, and then perhaps you'd also have the DLLs that exe needed, and these are kept together. And one benefit you have of keeping these together is that you can duplicate this container, and then you can have it run independently, simultaneously, multiple times. Now, duplication of containers like I'm describing can be for redundancy, but it's also for scalability. In fact, this ability for us to duplicate containers and run them multiple times is one of the inherent benefits you get from containerization. One reason containers are so popular in the dev community is because of the large task of managing a compatibility matrix. Now, without turning this into a course on compatibility matrix, when you're responsible to maintain multiple applications and make sure that they're all compatible with the underlying operating systems, you have to look for ways to simplify this, what some people refer to as the matrix from hell. Containers simplify this task by integrating pretty much all, if not most, of the dependencies within the container. So because of this, they really become very portable, and there's much less dependency on the operating system on which they run. So the dependency becomes more focused on the version of Docker, which is easier to maintain than versions of operating systems and other dependencies that would be on multiple hosts. So as I mentioned, containers are, in general, smaller instances of an app. And as such, there's typically many instances of the same container running, preferably on different hosts or servers. There are so many reasons this concept of lots of littles works so well. It works so well, it's becoming a standard for application development all over the world. So welcome to the new world of application development, containerization. Let's review some benefits. First, a smaller instance costs less in terms of resources and financial cost. Second, when you build a large app and it's comprised of lots of little smaller containers, a single container failure is a relatively small issue, and the app should still continue to satisfy user requests based on the other containers that are still running. Third, when you want to upgrade an app, you can simply deploy the newer version of your code to a new set of containers. This is really a very different way to upgrade systems than our traditional grab the server and upgrade it methodology. So what you do is you spin up additional containers with your new version of code. You send some test users to this new application pool, or perhaps you send a small percentage of real production users to the new application pool. This way, if the app is failing, only a relatively small number of users is affected. This is actually a very large concept I've described here, which we're going to discuss later. It's an entire topic called continuous integration and continuous delivery. You might have read CI/CD. In larger production environments, there's so many applications and so many changes occurring. The change management system becomes a pipeline, and this is what's known as a CI/CD pipeline. So we'll discuss that in more detail later, but for now, just understand there is a lot of value in making the large application being comprised of many smaller instances. This, in fact, is another huge benefit of containers, being small and having many of them. Another fundamental aspect of containers is they are usually stateless. Now, they can be stateful or they can be stateless. The majority of containers are usually stateless, and this is another critical concept to learn. See if this example makes sense. The data that an application usually serves is usually not on the server, the web server, for example, that's hosting it. This is not really a new concept. In the traditional sense, we've always had three-tier applications, in which case you've had a web tier, which interfaced with the user to get requests, deliver content, right, to the browser. You've had the presentation tier, which is its job is really to build the content into a viewable format. Just think of graphs and formatting the data. And then, of course, we've had the database tier, or the back end. This is usually where the data lives. So the most common use of containers operates on the same premise, where the web tier could be a simple container running a web server. Its entire job in life is to get requests from users and relay that to the back-end servers, and then deliver the content that it gets back to the user. From this point of view, the web server is disposable because it's not really doing anything special that another copy of that same web server couldn't do. If this is clear so far, that the data shouldn't be on the user-facing tier, you can see how we can scale horizontally by specifying that we would want X, let's say, front-end servers, and suddenly Kubernetes would spin up an army of web servers ready to interface with the user requests. Similarly, we can increase the instances on the backend servers as well. So this is, again, a fundamental benefit of containerization, and it contributes to something called horizontal scale. So here we are, having reviewed so many benefits of containerization, but I have to say this topic of containerization is so important. I'm going to go through a quick review again of all these benefits that containerization provides. This is just so important. Let's discuss the many benefits that we've talked about that containers provide. First, they provide portability. And this they provide via the ability to move a container to a different operating system without too much dependency on the operating system. As long as you have Docker installed, for example, on both operating systems, you can actually move a container from a Linux host to a Windows host, and the container would still run. Another benefit we talked about is stability and compatibility. Because the required dependencies are included in the container, this really results in a lot more stability. Now, another thing we spoke about is upgradability and change management. Remember, there's the entire CI/CD pipeline method in which you can upgrade servers, where you don't actually upgrade the instances of the app that are already running. You actually build new containers and you send a partial amount of your users to those. So this really leads to the next benefit, which is risk reduction and app uptime. Apps can remain up even when containers are failing and even when applications are being upgraded. Let's talk about continuous delivery. So as we discussed, you can upgrade application components while the app is still live. One of the benefits is that that larger application is going to get rewritten in smaller sections. A containerized app is usually smaller than the monolithic app. And what I mean is a monolithic app is a very large app where everything that the application needs to do happens in pretty much one executable. Because of this, it's compiled together, and making changes and upgrades usually affects other aspects of the app. In a micro app, the application is split with multiple different types of containers doing different roles within the app. And because of this, we can upgrade some of the application components while not touching others. This is another benefit that allows us to keep the application running even while we're upgrading portions of it. And the last thing we talked about was scalability. Because instances are relatively small, and because you can spin them up with automation, you can scale your applications with the quantity of containers running in a matter of seconds. Having a good understanding of why you need containers is very important. Once you have this, the next critical aspect of containers is how do you actually spin them up and how does this all relate to Kubernetes? So let's now go a little bit deeper into what's called the container runtime. The container runtime is basically the software that lets us spin up containers in a very simple and secure way. So I'm going to make a bold statement and I'm going to say Kubernetes really would be nothing if we didn't have the containers. So remember, Kubernetes is an orchestration tool and it's an orchestration tool for containers. So without containers, Kubernetes would really serve very little purpose. Now, if you appreciate what I'm saying so far, you realize that containers are pretty much the most important fundamental building block of a Kubernetes environment. So the software chosen to run the containers is critical. So this is why we're going to talk about Docker. Let's give the huge credit where credit is due. Docker has become the leader in building and running containers. So you may not have realized this before, but yes, it is Docker that builds and runs the containers in any Kubernetes environment. So there are other container runtimes out there other than Docker, and they might gain popularity and take over, but currently Docker is leading the way. So as such, probably every container out there is supported by Docker. So what is Docker? Docker is the system that interprets the container specifications and actually runs the container in the isolated way that we spoke about on the host computer. So as you should understand by now, Docker can and does run containers without Kubernetes. Kubernetes, like I mentioned, is an additional layer on top of Docker to provide high scalability, automation, and other advantages such as orchestration for container environments. Docker has their own product, in fact, that competes with Kubernetes called Docker Swarm, which is a great orchestration tool, but clearly the industry has preferred Kubernetes, and that's why Kubernetes has become the chosen leader. Now, as you should know by now, Kubernetes cannot operate without containers. And second, Kubernetes cannot operate without having something handle the containers themselves, such as Docker. So this is what we refer to as a container runtime, and Docker is the container runtime that I'm going to show you in my demos. At this time, you might be wondering why you even need Kubernetes if Docker is actually running these containers. But we'll get into that in due time because Kubernetes does provide significant benefits on top of just having containers.